Hello everyone. Today we are going to talk about a theorem which talks about or which gives an upper bound on the number of C4 free graphs on n vertices. The theorem and its proof which we are presenting are actually taken from lecture 6 of the lecture series on container methods by Jozsef Balogh. The theorem was originally proved by Kleitman and Winston in 1982. They proved that the number of C4 free graphs on n vertices is at most 2 to the power 1.08 into n to the power 3 by 2, and we will prove the same thing asymptotically by graph container methods. Before moving on to the proof, let's look at some definitions and notations. First of all, what is a C4 free graph? So C4 free graph is nothing but a graph which doesn't contain a cycle of length 4 in it. So for example, this a simple C5 can also be a C4 free graph. It doesn't contain any cycles of length 4. But on the same graph, if you put an edge between them, then this will not be a C4 free graph as it contains a cycle of length 4 with these 4 vertices. The next definition is what is mean degree ordering of a graph. So for a graph on n vertices, the mean degree ordering of a graph, which is stated as is a permutation of the graph of the vertices of the graph or an ordering of the vertices of the graph, which is Vn to V1, such that any vertex Vi is the minimum degree vertex on the graph induced by the vertices Vi to V1 in the mean degree ordering. So you can think that we can obtain a mean degree ordering of the graph by iteratively selecting the vertices of the minimum degree, removing it from the graph and its corresponding edges, and in the remaining graph again select a vertex of minimum degree, remove it from the graph, add it to the list, and continue so on. So just for a quick example, uh, if this is our original graph, then and if the numbers are 1 2 3 4 5 6, then what we do in this graph, we find the vertex with minimum degree. So there are many possible minimum degree vertices here. Currently the situation is we have two of them, which is 1 and 4, and they have degree 2 of them. So we remove those vertices from the graph. Let's say we remove 1. So we say remove 1 and its corresponding edges from the graph. We add 1 to the list. In the remaining graph, we again try to look for vertex, minimum degree vertex, which is again there are two of them, 4 or 3. Let's say we remove 3. We added 3 to it. In the remaining graph, we again look for the same. We look for 4. We remove 4 and add 4 to the list. The remaining graph, all of them have the same degree, so we can just arrange them in any order. Let's say we do it on the basis of in the reverse ordering of the basis of the names. So after removing all of them from the graph, the ordering will be something like 6, 5, and 2. Now the next definition is what is square of a graph? For a graph G, the square of a graph, it is denoted by G square, is defined on the vertices of the graph such that for every distinct pair of vertices U and V in G square, the multiplicity of the pair UV in G square is the number of UV paths of length 2 in G. So in simple terms, how we can obtain a graph or a square of a given graph is like following. Let's take an example. If this is our original graph on 8 vertices, it's a cycle of length 8. Original graph, which is G, then in G square, we will have the same graph, that is this one. But in addition to this, will have edges between every pair of vertices which have a common neighbor in the original graph, that is G. So the additional edges will be like this. So this is how G square will look like. One thing to note that by adding edges, we are also creating new pairs who have a common neighbor in G square. But basically we don't do anything to them. We only add edges between the pairs of vertices which have edges which have a common neighbor in the original graph, that is G, not in G square. This has to be kept in mind. Coming back to the proof of the main theorem, the flow of the proof goes like this. First, we will state a proposition and give its proof. We state a lemma then and prove it. And combining the results of this above two together with the container theorem for the graphs, we obtain the result which actually bounds the number of C4 free graphs in n vertices. One point to be kept in mind is that the lemmas and the propositions has been numbered exactly with the numbers as they have been mentioned in lecture 6 scribe notes. It will be easy. It will be then easy for the audience to tally the lecture 6 scribe notes with this video. Uh, Now let's look at proposition 1.3 and its proof. So what is the statement? It says that if G is a C4 free graph on n vertices, and if Vn to V1 is the min degree ordering of G, then for any Vi in the min degree ordering, the neighbors of Vi in Gi, in graph induced by the vertices from Vi to V minus V1, forms an independent set in Gi square minus 1. What it says that for any vertex V, the neighbors of Vi in graph Gi, where Gi is nothing but graph induced by vertices Vi down to V1 in the min degree ordering, the neighbors of Vi in this graph forms an independent set in the graph Gi square minus 1. So this is nothing but G square of vertices square graph formed by the vertices Vi minus 1 down to V1. Now let's look at the proof of proposition 1.3. So we'll prove it by contradiction. Suppose that the above statement is not true. Then for any Vi, there exist two neighbors of Vi, let's say x and y, such that they have an edge between them in the square graph Gi square minus 1. So basically, Vi will have two neighbors x and y such that they have an edge between them, which is like this one. And this is the contradiction saying. Then, by the definition of the square of a graph, x and y will have an edge between them only if they have a common neighbor in Gi minus 1. Let's say that this common neighbor is z. One thing to be noted is that z is not Vi. Z cannot be equals to Vi because we are only considering the graph Gi minus 1. So Vi doesn't come into the picture. So from that we can conclude that apart from Vi, these two vertex x and y have a separate neighbor in the original graph G, which is z, which means that together Vi, x, y and z will form a C4, thus contradicting the statement of the proposition, which is G is C4 free. So this concludes the proof of proposition 1.3. Next, we will look at lemma 1.4 and my group mate Dinesh will continue from here.
Now let's take a look at lemma 1.4. Let's construct a graph G with m vertices such that the minimum degree of graph G is small d, and let n be n the number such that n greater than m and m is greater than or equal to small d, and let h denote the square graph of G. Now let's take a subset of vertex set of G and denote it by J, and let the J be selected in such a way that its size is at least 4n by d. Now the lemma states two results. One is the size of edge set of h of j, which is the number of edges of h which include only the vertices in j, is greater than or equal to d square into cardinality of j square divided by 4n. Furthermore, we also have another result, uh, which is only true when the graph G is C4 free. So when the graph G is C4 free, then the average degree of h of j is greater than or equal to d square into cardinality of j divided by 2n. So now let's prove lemma 1.4. So for this, I'll be using a notation bj, which denotes the degree of vertex vj formed by vertices in J. So let me elaborate on this. Suppose we have our vertex Vj and we have some of its neighbors 1, 2, 3, and 4, 5. So only 3, 4, 5 belongs to J and 1, 2 does not belong to. Then Vj will be only 3. As 1, 2 does not belong to J, we'll only be considering the vertices which are in J, which are 3, 4, 5. So the Bj will be 3. So right now let's calculate the sum of all bj's, which will be the sum of all the degrees of all vertices which are induced only by vertices in G. So from the perspective of all vertices, it's looking complex. So let's change our perspective from other vertices to the vertices in G. So as we are calculating for all the vertices which are present, uh, the all neighbors of vertices in J will be calculated at least once for that particular vertex. So let's take an example. Suppose we have 1, 2, 3, and we have 4, 5. So now when we calculate B1, we'll be calculating these two, and we are calculating B2, we'll be calculating these two, and we are calculating B3, we'll be calculating these. So from this perspective of all vertices, these are the edges which will be contributing towards the BG. Now, when you look at the perspective of 4, all its neighbors, which are 1, 2, 3, outside of J, right now, are being calculated. So, when we take a sum of all the BJs, we can actually replace the whole thing by the sum of all the degrees of vertices which are present in J, which is being shown here. So, here V is a vertex which is present in J, and dg of V is the degree of that vertex in the actual graph with G. So as our minimum degree of what graph G is small d, this is greater than or equal to cardinality of J into D, and as n is greater than or equal to small d, this result will be obtained. So no, next let's actually take a look at what is uh, E of J. I mean, E of H of J has been told very vaguely. So let's take a closer look. As I already explained, uh, E of H of J is consists of only the edges which are formed only because of the vertices which are present in J. So if we have some vertices, and there are lots of edges, and J belongs to a subset, then we'll only be considering the edge which are formed due to the vertices which are present in G. and this is here denoted by an indicator random variable xuv, where xuv is only one if there is an edge between u and v and both u and v belongs to j and zero otherwise. So using this we can actually calculate the value of e of h of j. So let's calculate the actual value. Now as I've already said, e of h of j, h is g2, that is only formed by edges which are of length 2. I mean, suppose there are two vertices u and v. U and v will have an edge in H only if there is a path between u to v with length of 2. So using that notation, we'll move forward. So for this to happen, we need a vertex, some v x, which is a common neighbor to both u and v. So now let's take a look from the perspective of x. So for u and v to have an edge, it needs to be common neighbor of both u and v. So x has b x number of neighbors in j. So for these edges between u to u v to happen, we need to select two vertices from j which are neighbors of bx, and they too will have an edge between them in h of j. So suppose there are two vertices and this is Rx, and for n1 and n2 have an edge between them. These two needs to be the neighbors of x. So the number of ways to select these n1 and n2 is going to be bx choose 2. So moving forward, this is only for a single vertex. So when we take the sum of all the vertices which are present in graph G, this is the expression which we'll be getting. And this is greater than or equal to this value using inequalities. And as sum of bj's is greater than or equal to cardinality of j into d, as we have shown in the previous slide. And if we expand this, we'll be getting this result. So now we have shown that e of h of j is greater than or equal to d square into cardinality of j square divided by 4n. So now from proposition 1.3, if a graph G is C4 free, then graph G2, which is H, is a simple graph. So we will be using this. We know a property that for a simple graph, the average degree is 2 times the total number of edges divided by total number of vertices. So we will be using that. We have already shown that E of H of J is greater than or equal to D square into cardinality of J whole square divided by 4. This is what we have shown already. 4n, sorry. So this is what we have shown. And when we multiply this into 2 by cardinality of j, this is the result which we will be getting. So from this we have shown the second part of the lemma, which is d of h of j is greater than or equal to d square into cardinality of j divided by 2n. So now let's move on to the actual proof of the given problem statement. Now the given problem statement can be divided into two cases. Uh, for this, I'm using a notation di, which denotes the degree of vi in gi. As you recall, gi is the graph which is formed by vertices v1 to vi, where all the vertices form the main order sequence. So right now there are two possible cases. One is when di is less than root over n by log n, and another is when di is greater than root over n by log n. So now first let's take a look at when di is less than root n by log n. So when di is less than root n by log n, for a given vertex vi, we can choose its neighbors uh, in n choose di number of ways. As di is the degree of the given vertex and n is the total number of vertices, n choose di is the total number of ways which we can select its neighbors. And there is a proposition which states that if we know the min order sequence and the neighboring set, it actually determines the graph. So let's move on forward. Um the number of ways which we can select the neighbors of vi is n choose di, and as di is less than or equal to root over n by log n, this is if we directly substitute it, we'll get this. And using an inequality that n choose r is less than or equal to n power r, if we substitute that, we'll get n power root n by log n, which is order of 2 power root n into log n by log n. These two gets cancelled, and we'll finally get the result of less than or equal to 2 power root n. And if di is greater than or equal to root n by log n, the case is a bit complex, for which we'll be using graph container method. And after we apply graph container method, we'll get these following these results. So the cardinality of our certificate, I mean, the number of vertices in our certificate will be less than or equal to log square n, and the size of container is less than or equal to 4n by di. This is the results which we'll get after applying the graph container method. So now let's take a look at what are the number of possible ways or number of independent sets in the graph h I minus 1, h of uh, or more precisely g2 of I minus 1, which is formed only by the vertices of v1 v2 so on v I minus 1, and we will taking a square graph on this. So there are two parts over here. One is this and another is this. So this part is formed by the number of ways which we can select our certificate, which is uh, and choose the cardinality of certificate, which is this value. And for a given certificate, we have our container, and in the container, we have uh, an independent set of size di, and the number of ways in which we can select that independent set is going to be the cardinality of C container. Wait a minute. Cardinality of container choose log di. This this will be our number of ways which we can select our independent sets for a given vertex vi. So, and the cardinality of ci is less than or equal to 4n by di. So if we substitute that, this is the whole result which we'll be getting, and this value is less than or in the order of 2 power root n. So right now we have proved that for given vertex vi, we can select its neighboring graph in the order of 2 power root n. So by using this, we'll show further proof that the number of C4 free graphs is 2 power order of n power 3 by 2. So for this, we'll be selecting we'll be going one after the other. First, let's assume we have already shown that for a given vertex vi, we can select its neighboring set in the or in 2 power root order of root n ways. Now this is for a particular vi, and we have n such vertices. So that will be 2 power order of root n into 2 power order of root n, and so on. This will be multiplied n times. So on a whole, we'll get the result, which is 2 power order of root n whole power n, which is 2 power order of n power 3 by 2. This is a very loose bound, but this is an upper bound. So next, as I already said, that there is a theorem which says that if we know the main ordering sequence and the neighboring set of all vertices, then the graph is fixed. So using that, we can say that the all number of graphs which are possible in this construction is going to be our total number of C4 free graphs possible. So here you can clearly see three terms: n factorial, n power n, and 2 power order of n power 3 by 2. So um, first we have our minoring sequence, which is v1 less than v2 less than vn. Wait, vn. The degree of vn is less than degree of vn minus 1, so on, less than vn. These can be selected in n factorial ways, and for each vi, the di is not fixed, and this can be chosen in 0 to n. There are n possible ways. So this is for a particular vertex vi, and there are n such vi's. So n into n into n, so on. This is multiplied n times. So from there we will get n power n. So these are the three terms. First term is formed, n factorial is formed due to the number of ways in which we can select our min-ordering sequence, and n power n is formed due to the number of ways in which we can select the degrees of the vertices, and n power order of n power 3 by 2 is formed due to the number of ways which we can select our neighboring set for a given vertex in whole. So this will be 2 power n log n plus n power 3 by 2, and n log n is far lower than n power 3 by 2 as n goes close to infinity. So we can approximate this into the order of n power order of 3 by 2. So that's all. Thank you.